All right, welcome engineers. In this explainer, we're going to get right into the nuts and bolts of how a computer actually sees. We're going to start from the ground up, literally, from the single pixel, and then build our way to the classic techniques that let us pull real, meaningful information out of an image. Let's dive in.
So, here's our roadmap. We'll start with the language of color itself, first with the foundational RGB model, and then we'll look at a much more intuitive way to think about it with HSV. After that, we'll jump into how we actually find things in an image, putting two old-school heavyweights, Hogg and Sift, head-to-head.
Before we get into any fancy algorithms, let's just pause and ask the most basic question of all. You and I, we see a picture of a duck, but a computer, it just sees a massive grid of numbers. So what really is a digital image from the machine's point of view?
Okay, everything, and I mean everything, starts at the lowest possible level, the pixel. And the model that underpins basically every digital display you've ever looked at is RGB.
At the end of the day, any digital image is just a big spreadsheet, a grid of these tiny little squares called pixels. The whole magic trick is in how we tell each of those little squares what color it's supposed to be. And we do that with a set of numbers we call pixel intensity values.
So take a look at this duck. To our eyes, it's a flat two-dimensional picture. But to the computer processing it, this is actually a three-dimensional data structure. You've got the height and the width of the image, sure, but there's also a third dimension. And that third dimension is where all the color information is hiding.
So what is this third dimension? It's not depth like in a 3D movie. Instead, it's actually three separate layers, or what we call channels. There's one for red, one for green, and one for blue. The final color of any single pixel is just a mixture of the values from those three channels.
And this is a really cool way to visualize it. You can actually pull the image apart into its components. Now, what you're seeing here for the red and green channels aren't actually red or green images. They are grayscale intensity maps. A bright white area on the red channel just means, hey, for these pixels, turn the red value all the way up to 255. A black area means turn it down to 0. This is the raw data. And here's the last piece of the puzzle, the blue channel. The easiest way to think about it is like you're stacking 3 sheets of transparent film. You layer the red, green, and blue intensity maps on top of each other. At every single coordinate, the 3 values add up to create that one specific color that we see in the final image. Okay, so RGB is essential for displays. But for doing any kind of analysis, it can be a real headache. I mean, think about it. If I asked you to programmatically find all the green pixels, you'd have to write some messy code to define a valid range for R, G, and B, and it would probably fail in different lighting. This is exactly the kind of problem that the HSV model was built to solve.
HSV stands for hue, saturation, and value. And what it does is it smartly remaps RGB into components that make way more sense to us as humans. You have hue, which is the pure color itself, red, orange, yellow, and so on. Then you have saturation, which is how vibrant or washed out that color is. And finally, value, which is just a simple measure of its brightness.
And this color wheel is why HSV is so powerful. Notice how hue is just an angle on the circle? It has completely decoupled the idea of what color is it from how bright is it. So now that tricky problem of finding all shades of green becomes dead simple. You just tell the computer, give me every pixel with a hue between, say, 60 and 180 degrees. That's it. It makes things like color-based segmentation so much cleaner.
Okay, so we've nailed down how we represent an image with numbers. But that's still just raw data. How do we get the computer to actually understand what's in the image, to find a face, or a car, or our duck? To do that, we have to move up from pixels and start talking about features.
Now, in the modern era of deep learning, you just throw a giant convolutional neural net at the problem. But before that was an option, engineers had to handcraft these feature extractors. They had to explicitly design algorithms to find meaningful patterns. We're going to look at 2 of the most significant techniques from that era, the ones that really laid the groundwork for everything that followed, Hogg and Sift.
So both of these algorithms are trying to do the same thing, create a compact numerical description, a feature vector, for a part of an image. But they go about it in completely different ways, and that, of course, leads to a classic engineering trade-off.
Let's start with Hogg. That stands for Histogram of Oriented Gradients. The core idea here is all about capturing shape by looking at edges. The algorithm chops the image up into little cells. In each cell, it calculates the image gradient, which is just a fancy way of saying it finds the direction and strength of edges. Then it makes a little histogram counting up how many edges point in each direction. You chain all those histograms together and you get one big vector that describes the object's silhouette really well.
Now, SIFT takes a totally different tack. SIFT, or Scale Invariant Feature Transform, doesn't care about the overall shape. Instead, it looks for very distinct, high-contrast points in the image, like corners or unique textures. It calls these key points. For each key point it finds, it creates a detailed descriptor of the area right around it. And it does this in a way that's incredibly robust to changes in scale and rotation.
So here's the fundamental philosophical divide. HOG gives you a dense descriptor. It's describing the shape of the whole object. That's why it was so famous for things like pedestrian detection. SIFT, on the other hand, gives you sparse descriptors. It ignores most of the image and just hones in on a few really stable points. This makes it perfect for things like creating a panorama, where you need to match those exact same points between two different photos. This table really boils down the trade-offs. The big win for SIFT is right there at the top, invariance. It handles changes in scale and rotation, which HOG does not. That makes SIFT more accurate for many tasks. But, and it's a huge but, look at that bottom row. Both of these are computationally expensive. They required a lot of horsepower, which was a major limitation in practice.
And that was really the key bottleneck. For as foundational as they were, HOG and SIFT are slow. They're mathematically complicated to implement from scratch, and they each have their own weak spots. HOG, for instance, can be very sensitive to changes in lighting or even just a little bit of image blur. All of these drawbacks created a clear demand for something better.
And this leads us to the final thought. The slowness, the complexity, the rigidity of these handcrafted feature detectors created a massive engineering problem. It begged the question, what if, instead of spending all this time meticulously designing algorithms to find edges and corners, what if we could just let the machine learn which features are important directly from the data itself? That question, born from the limitations of these very techniques, is what set the stage for the entire deep learning revolution and the rise of the convolutional neural network.